Hello everyone, welcome back to Math with Allison. Today we're going to do an exam. So this would usually be the third exam in the calculus series depending on your professor, but this one is going to be on the back end of all the derivative stuff. So intervals of increasing, decreasing, concavity, optimization, stuff like that. So let's go ahead and go through it. So like I said, this is a real exam given to me by a professor who I've worked with. This was given in the fall of 2017, and this person now releases this to their current students for them to study. So notice here it says that the exam has 6 questions totaling 100 points. Typically, we don't care how much you simplify it down. As long as you do the calculus part, usually you're good to go. But there are some instances where we do take off points, like if you just leave it as cosine of pi, natural log of 1, or e to the 0. Things like that should be simplified, but if it's like 100 divided by the square root of 51, we do not expect you to simplify that down. So just be aware of stuff like that. Okay, so let's just go ahead and go through this. So for the first question, we want to identify its indeterminate form, then evaluate this limit using L'Hopital's rule. So always make sure you read the directions because it's very easy to skip over the indeterminate form part. But if I were grading this, I would have to take off points because the question asks for it if you don't provide it. So first, what we always want to do first is try direct substitution. So here, let's just go ahead and plug in that value 1. So if we notice here, this goes to 0 over 0. This is our indeterminate form, which tells us we can use L'Hopital's. So I'm just going to go ahead and give that little symbol. That means I know I'm taking L'Hopital's, and now I take the derivative of the numerator and the denominator. So here we get negative 2 minus 5x to the power of 4 divided by 6x squared minus 3. So typically you want to make sure that it's simplified. In our case, I don't see how much more simplified it can get, so we can go ahead and try using direct substitution again. We're going to go ahead and plug in that value 1. So here we get what our limit is equal to, and that's negative 7/3. So let's go ahead and try part B. Of course, we're going to go ahead and use direct substitution first. We plug infinity in, we get the square root infinity divided by the natural log of infinity. Of course, this is all theoretical. Infinity is just a concept, but we're just trying to look for that indeterminate form. So this goes to infinity over infinity. So like I said, it's theoretical. Don't get mad at me for plugging it in. It's just trying to picture what's going on. So let's go ahead and apply L'Hopital's rule. So I'm going to write down that we're doing that. So remember, the square root of x can be rewritten as x to the power of 1/2, which tells us we can use power rule. So I'm going to bring down that power and then subtract 1. And then the derivative of natural log is 1 over x. So let's try to simplify this first because we got a lot of fraction action going on. So the limit as x approaches infinity, I'm going to rewrite the numerator as 1 over 2 times x to the 1/2. So I just bring that power down. And instead of writing it as a fraction, I'm going to say it's divided by 1 over x. Because remember, when we divide, that actually means we get to multiply by the reciprocal. So here, notice we can simplify this out a little bit. These x terms simplify, so that's an x to the 1/2 in the numerator. So here, I'll go ahead and rewrite it. We have the limit as x approaches infinity, x to the 1/2 in the numerator and 2 in the denominator. So let's go ahead and now try to plug in the value of infinity. If we plug it in, it's like taking the square root of infinity divided by 2. And the square root of infinity is infinity. Infinity divided by 2 is infinity. And so this whole thing is just equal to infinity. Okay, so here we have one that's a little interesting. Notice that we have this 1 over x in the exponent. So whenever you see the variable in our exponent, we want to go ahead and use a logarithm in order to get that out of the exponent. So I'm just going to go ahead and set this whole limit equal to y. Because what I'm going to go ahead and do is I'm going to take the natural log of both sides. And I can pull that natural log inside of the limit. So here we get the natural log of 1 plus 2x to the power of 1x. So remember, the point of taking the natural log is using natural log rules, which tells us this can come out front and multiply by it. So with L'Hopital's rule, we want this to look like a form of a fraction. So I'm going to go ahead and rewrite this as a fraction. In the numerator, I have the natural log of 1 plus 2x, and in the denominator, I have x. So now let's go ahead and try direct substitution on the right side of this limit. Here we get the natural log of 1 plus 0 divided by 0, which this goes to natural log of 1 divided by 0, and we know the natural log of 1 is equal to 0. So here is our indeterminate form, that is 0 over 0. So what we can do is go ahead and take L'Hopital's rule. So here we need to take the derivatives. So I know that x in the denominator goes to 1, but in the numerator we're going to get a fraction. So whatever is inside the natural log goes on the bottom, and the derivative goes on the top. So the derivative of 1 plus 2x is just 2. So let's go ahead and try direct substitution now. Here we get the natural log of y is equal to, and this becomes 2 over 1 plus 0, which is just equal to 2. So that means the natural log of our solution was equal to 2, and we want to go ahead and raise both sides to e. So here that cancels out with a natural log, and we're left with y is equal to e squared. And then that is our solution, e to the power of 2. And the reason why I leave it as y is because we set y equal to our original limit. Okay, so here for part 2, we have the function 2x minus 5 over x squared. And first, we want to go ahead and find the derivative. So in order to find the derivative, we're going to go ahead and use quotient rule. So I'm going to go ahead and set that up. Okay, so let's find these derivatives. First, we get 2, and then for g, we get 2x. So in order to find f prime x, we are going to go ahead and start at the bottom, work our way to the top. So here we get 2x squared, and now we subtract. And now we do the opposite multiplication. So 2x minus 5 times 2x. And then all of this will be divided by the denominator, x squared squared. So let's go ahead and simplify this down. So here, let's go ahead and multiply in this 2x. So we get minus 4x squared plus 10x. When we have a power to a power, so x squared squared, we just multiply those powers together. So we get x to the power of 4. So let's go ahead and simplify this down. Here we get negative 2x squared plus 10x. So I'm going to plot an x in the numerator. We're left with negative 2x plus 10. This is getting closer to what we're looking for, right? Divided by x to the power of 4, which means we can cancel out one of those x's. So here we get negative 2x plus 10 divided by x to the power of 3, which is exactly what we were trying to show. So now that we showed this, let's go down to part B. We want to go ahead and make a sign chart and use the sign chart to fill in these answers on the right. So first what we want to do is find the critical values. Notice here that we have an x cubed in the denominator, which means we have an illegal value at x is equal to 0. We have to make sure to include that in our critical values. So now what we can do is set our function equal to 0, which is the same as just setting the numerator negative 2x plus 10 equal to 0. So here we got another critical value. So this tells us we have two critical values at x equals 0 and at x equals 5. So now we're going to go ahead and set up the sign chart. So here I'm going to draw it out. We fill in our critical value. So we have one at 0, we have one at 5. Notice that this critical value is going to be a bit different because this is going to be a vertical asymptote. So make sure that we're aware of that. But otherwise, we are going to go ahead and test values from each interval. So let's choose -1, +1, and 6. We're going to plug those into our first derivative because if it's positive or negative, that tells us if our function is increasing or decreasing. So I'm going to go ahead and test these three values into our derivative. Okay, so in our first interval, I got -12. In the second interval, I got +8. And in the third, I got -2 divided by 6 cubed. I don't know what that actually equals. All I care is if it's positive or negative. So that tells me first we are decreasing, we switch to increasing, and then we are again decreasing. So now let's go ahead and use a sign chart to fill out these questions over here. So we are increasing on the interval 0 to 5, and we are decreasing on two intervals, so -infinity to -1, and also union 5 to infinity. So a local maximum occurs right here at x is equal to 5, and we can see that from the sign chart. And we would think a local minimum occurs at x equals 0, but remember this was a vertical asymptote. So actually our function is not defined at that value. So here we would have none. So that could be a little trick question to get you. Make sure we pay attention to our illegal values. So here we have some miscellaneous questions. So first we want to find all intervals on which this function is concave down. So in order to solve for concavity, that means we need to get to the second derivative, right? Here we take the first derivative, we get 12x minus 3x squared. We can take the second derivative and we get 12 minus 6x, and we can set this equal to 0. So here I add over that 6x, divide both sides by 6, and here we get our inflection point. So I'm going to go ahead and do a sign chart because those are my favorite. I'm going to plug in our critical value, and what we're going to do is test points from each interval. So let's go ahead and try 0 and 3. So I'll go ahead and plug in those two values. So when I plugged in 0, I got a positive 12, and when I plugged in 3, I got negative 6. So that tells me my function is concave up on this first interval and concave down on the second one. And so our question wanted us to answer which intervals it's concave down. So that would be from 2 to infinity, and I'll go ahead and box it. Part B is asking us to rewrite the sum using sigma notation, and we don't have to evaluate it. So remember, there's so many different ways that you can write a sum. The first thing I notice here is that everything is raised to the power of 3. And I also notice that I'm counting up, starting at 2 and ending at 8. So this means this is going to be the sum of our number raised to the power of 3, and we start at 2 and we end at 8. And so that is one way that we can write out the sigma notation. Remember, I said there's multiple, so this is not the end-all be-all, but it's one great way. Okay, so let's talk about the mean value theorem. So here it's asking what two conditions must be satisfied in order to apply it. The first one is that f must be continuous on the closed interval a to b. The second part is that f must be differentiable on the open interval a to b. So if those two conditions are satisfied, then we can go ahead and use the mean value theorem. So here they tell us what the mean value theorem says, and it tells us that we want to use the function x squared on the interval 1 to 4, and we want to find value c that makes the theorem true. So let's go ahead and plug in our endpoints. First, I'm going to plug in f of 4. Here we get 4 to the power of 2, which is 16. I'm going to do the same thing with our other endpoint. We get 1 squared, which is equal to 1. So if I set up this first part, we get f of 4 minus f of 1 all over 4 minus 1. So this is equal to 16 minus 1 over 4 minus 1, and this is going to be 15 divided by 3, which is just 5. So now let's go ahead and do the second part of this. I want to go ahead and take the derivative. So here we get 2x. I'm going to go ahead and set the derivative 2x equal to what we got right here, so 5. If I divide both sides by 2, I get x is equal to 5 halves, and this is the value that satisfies the mean value theorem. And we know this is for sure good because it's also inside our interval 1 to 4. So here's our solution. Okay, so here we have optimization problems. I'm going to do both of them, but I'm going to start with this left one first. So we have this picture of a rectangular pen, and I know it has to enclose an area of 300 square feet. The front of the pen is to be made with a cost that costs $10 per foot, and then the sides and the back, everywhere else, is going to be $5 per foot. So what should the dimensions of the pen be in order to minimize the total cost of the fencing? So for full credit, we have to show that we found the actual minimum. So let's go ahead and do this thing. I'm going to go ahead and label all the sides. So I'll just call the front and the back x, and then I'll call the sides y. And what we're going to have here is the equation that we're trying to optimize, which in this case is going to be the cost. And we're also going to have our constraint, which is going to be the area. So let's go ahead and write this out. I know the cost of our function is going to be 10 times x, because it's $10 per foot in the front, plus each side is going to be $5 per foot, and then the back is also going to be $5. So we can go ahead and simplify this. We get 15x plus 10y. Remember, we're going to have two equations in this case, so our constraint is going to be the area. So we know that x times y is going to equal 300. So since we're trying to optimize the cost, I want to go ahead and make sure this is all one variable. Right now we have two variables, x and y. We know that we don't want to do implicit differentiation. I know how people feel about that. So let's go ahead and just solve for y in this case. So y is equal to 300 divided by x, or if you wanted, you could rewrite that as 300 times x to the power of negative 1. So let's go ahead and replace this y with what we just found it was equal to. So in our cost function, we get 15x plus 10 times 300x to the negative 1. Here we can simplify this one time if we'd like, and we get plus 3000x to the negative 1. So since we're trying to minimize the cost function, let's go ahead and set up the first derivative test. I'm going to go ahead and take the first derivative. So we get 15, and that becomes a minus 3000x to the negative 2. If you wanted, you could rewrite that as 15 minus 3000 divided by x squared. So what we want to do is solve for our critical value, and I'm going to do that by setting it equal to 0. So I'm going to add over that second term. And in order to get the x squared out of the denominator, I'm just going to multiply it over to the other side. So I get 15x squared is equal to 3000. Here I can divide both sides by 15. So I get x squared is equal to 200. I'm going to take the square root of both sides. And remember, I only care about the positive square root because we're working with area. We can't have like negative fencing. So here I'm going to simplify this one more time and I get 10 root 2. I don't really know if you need to simplify it. You could have just left it as square root of 200, whatever your heart desires. So I'm just going to erase this part real quick for room. Let's go ahead and set up our sign chart. So here we're not going to go into the negative area, so I'm just going to leave that at 0. And we're going to plug in our critical value of 10 root 2. And let's go ahead and find points that we can plug into our first derivative. And in this case, it's not going to be f, it's going to be c prime. And that's going to tell us what our cost function is doing. I know I can for sure choose a value of 10, and let's go ahead and choose a value of what, 20? I think those two are safe. So let's plug that into our derivative, which is going to be this right here. Okay, I hope you like my issues. So here, 30 divided by 4, I know 7 times 4 is 28, so it's going to be a little over 7. And here I'm just guesstimating because all I care about is if it's positive or negative. I know 8-ish is going to be a solid positive number. So that tells me on this interval I'm going to be positive. My other interval I got a negative value, which tells us our cost function switches from decreasing to increasing at our critical value. So here is proof that we found our minimum. So let's go back up and think about the question that is being asked. Here we want to show the dimensions of the pen in order to minimize the total cost of the fencing. It's not asking us to find the minimum cost, so that means I can go ahead and find my corresponding y value, and I'm going to use it with this equation right here. So x is equal to 10 times the square root of 2. That means y is equal to 300 divided by 10 times the square root of 2. You could simplify that if you wanted to. This right here would give you full credit though. So that is the first optimization problem. Also, a little side note, if you don't want to do the first derivative test, you could do the second derivative test. So you could look at the concavity, and if it's concave up, we know it's going to be a minimum. So let's go ahead and set up the second problem now. Okay, so here we can say a rectangle is constructed with one side on the positive x-axis. So I know that this length right here is going to be x. And then one side on the positive y-axis and the vertex on the origin. So here the curve is equal to y equals 10e to the negative x. So I know my height is going to be 10e to the negative x. So what is the largest possible area for such a rectangle? So let's go ahead and set up an equation. I know area is going to be equal to the length times the height. So here we get x times 10e to the negative x, which we can rewrite as 10x e to the negative x. Notice here, we're actually not going to have two equations because we're already safe. We are already working with only one variable, so we don't need to plug anything else in. I think that would definitely throw off students because you're used to having a problem, because you're used to having an equation to optimize and an equation that is your constraint. In this case, we're already in terms of one variable, so we don't need to do any systems of two equations stuff. So that means we get to go into direct optimization. So let's go ahead and take the first derivative. In order to do this, we are going to have to set up product rule. So I'll go ahead and do that. Okay, so the derivative of 10x is just going to be 10, and the derivative of e to the negative x is negative e to the negative x. I just multiply by the derivative of the exponent. So for a product rule, I'm going to go ahead and multiply these across 10e to the negative x. And that'd be plus, but because we have a negative right here, it turns into a minus 10x e to the negative x. Okay, so let's try to simplify this. I can pull out a 10, and I can also pull out e to the negative x. And here I have my leftovers, which is 1 minus x. And I want to go ahead and set this equal to 0. So we're going to apply the first derivative test. If you like, you can apply the second, whichever your heart desires. But that means I'm going to set both of these terms equal to 0. So first I get 1 is equal to x. And then over here I get 10 to the negative x is equal to 0. This is not going to ever give us a critical value because e to the negative x will never equal 0. So that means we only have one critical value. So actually, I think I just decided I want to try the second derivative test on this one. If you want, you can set up the line chart and do the first derivative test. But that means I'm going to go ahead and use product rule again because I want to find the second derivative. Okay, so here I get negative 10e to the negative x, and also I get negative 1. So let's go ahead and set up that product rule. I'm going to write it here on the left side. So the second derivative is equal to the first cross product, negative 10e to the negative x times 1 minus x. And I'm going to go ahead and add on this second cross product, which actually will result in a minus because of that negative. So minus 10e to the negative x. We could try to simplify this. I can pull out negative 10e to the negative x, and then I have my leftovers 1 minus x plus 1. So this is equal to negative 10e to the negative x, 2 minus x. Okay, so in order to see what happens at x equals 1, I'm just going to go ahead and plug that in. So the second derivative at 1 is equal to negative 10e to the negative 1, 2 minus 1. So this is equal to negative 10 divided by e times positive 1, which is just negative 10 divided by e. So this is going to be a negative value. A negative value tells us that it is concave down. And because it's concave down, that results in a maximum. So this right here would be my proof that I needed in this last sentence. For full credit, you must show how you know this is the maximum area. So right here, I just showed I know this is the maximum area. So I want to go ahead and find the actual area now. So I know x equals 1 is going to be your magical value. So let's plug that into our area. Here we get the area is equal to 10 divided by e. So that is our final solution. Okay, we get to practice our drawing skills here. I'm going to zoom out quite a bit so we can all see it. Here we are given lots of pieces of information, and we are going to fill in the chart. So first we have the domain is from 0 to infinity, and they already kind of included that in the graph. I don't go into the negative area. We also have that it's continuous with one x-intercept at 4, 0. So I'm going to draw in that x-intercept right here. So first we have the limit as x approaches infinity is equal to 3. So 1, 2, 3, that means we are going to have a horizontal asymptote at x equals 3. So horizontal asymptote, we also have the limit as x approaches 0 from the right. It's going to go up to infinity. So I'm just going to draw a little arrow there so I know it's shooting up. Let's go to the next sentence. Here we have that the first derivative is negative when x is between 0 and 4. So I'm going to go ahead and draw in that x equals 4. So I know on this side it's going to be decreasing, and now it's going to be undefined at x equals 4. And then when x is greater than 4, we have that the first derivative is positive, which tells us it's increasing. Now we have some information on the second derivative. We have between 0 and 2 that it's positive, so I'm going to plug in that value of 2. I just fixed the 4 thing, don't worry guys. Okay, so now we have that x is equal to 2. We have between 0 and 2, the second derivative is positive, which tells us it's concave up. And then we switch over to concave down. We have that it's undefined when x is equal to 4, and then negative when x is greater than 4. So it just stays concave down. So now I'm going to go ahead and use all this information in order to fill in the graph. So I know I'm going up to infinity, and then what I have is concave up but decreasing, and I switch to concave down and decreasing. Notice we're going to have that this is undefined, which means I'm going to have a cusp or corner, whatever you like to call it. And then I'm increasing, but I stay concave down, and I'm approaching that value of 3. So that is what our function would look like. Here is all my notes on the bottom. That's how I like to visualize it. It's very helpful for me. If you have a different way of doing it, that's great. Okay, we have one last problem here. So we have the function, and we want to find the absolute minimum. So let's go ahead and find the first derivative, f prime of x. This is equal to 4x to the power of 3 minus 8x and then plus 0. So what we can do is simplify this. I can pull out a 4x and I get x squared minus 2, and we can set this equal to 0. So this will give us some critical values. First, we have that x is equal to 0. Here we have that x is equal to the square root of 2. Notice I don't include the negative square root of 2, and that's because of the interval. That's not going to be inside the interval, so I can ignore it. So here, let's go ahead and set up a sign chart. I start at 0 and I end at 2, so I don't have to include any other values. And we're going to plug in our critical value of the square root of 2. So let's go ahead and choose 1, and we can choose 2 in this case. It's okay to plug in endpoints, because the reason I didn't plug in 0 was because that was already a critical value. In this case, 2 is not a critical value, and it's still within our interval, so I can still plug it in. So when I plugged in 1, I got a value of negative 4, so it's negative, and then when I plugged in 2, I got 16, which is positive. So that tells us my function is decreasing and then switches over to increasing. As we can see here, we for sure have an absolute minimum, so I don't need to worry about plugging in the endpoints. If I was looking for the absolute maximum, then I would want to worry about the endpoints, right? So let's go ahead and plug in the square root of 2 into our function so we can see what our minimum is. Here we get f at the square root of 2 is equal to So here we got the absolute minimum value of f of x on our interval is -3, which occurs at x equals the square root of 2. For part B, we want to find the linear approximation of f at a is equal to 1. So we're trying to find the line. In order to find the slope of our line, we want to plug in our derivative at our a value. So when we plug this in, we get 4 times 1 to the power of 3 minus 8 times 1. This is equal to 4 minus 8, which is -4. So we have our slope. We want to go ahead and find our 2 points. So first we have that x is equal to 1, so we can find our corresponding y value, which is when we just plug in 1 to the original function. So we have our x value, now we have our corresponding y value, so we can plug this into our equation. Y minus y1 equals the slope times x minus x1. Here we have our equation, so we can fill this in. We got L of x is equal to -4x plus 2. And that is our final solution. So that's all I have for us in this video today. If you enjoyed it, I have many more like it, so make sure to check out my playlist. They're linked down below. Otherwise, please give this video a thumbs up and comment other problems or topics you'd like to see done. If you're studying, I wish you luck. Thanks for watching.